So what we covered up to here is that we covered the axial load, and we look at what happened in the axial load, and then we look at what would happen if you have a torsion or torque moment in an object. The next two things that we are going to look at it, and basically the next is the bending, and then we are going to look at the shear. They are involved in lots of centroid finding and moment of inertia finding. So basically, like the previous one that we said up to here, they assume that you know the entire statics, that how you find the internal force or the internal moment. For the next two chapters, one more step will be added to it. Not only you need to know the internal force and internal moment, you need to be able to calculate the centroid and the moment of inertia, and then we have the Q for the shear stress. We'll get to that later. So because of that, I know we had that in statics, but I always reviewed these two topics because we're going to use them a lot. So I'm going to start to review them today. If you don't remember them, so it's a reminder. So first I will go to the centroid, how you can find the centroid again. Then I will go through the moment of inertia, how to find that. And then probably we're not going to have time. The next session I will start the bending. So first the centroid, look at how we can find the centroid. I'm gonna, anyway, this is the statics of the same books, so it's the same author. Just use that as a reference, so it's going to be similar to the strengths of material book that we have. For the centroid, remember that we could have find the centroid for the line if we had the line, or we can find the centroid for the area, or then we look at that, we can find the centroid or master of the mass or master of center of mass or center of volume if it's a 3D. In this entire the strengths of material, we deal with the cross section. So the cross section is always the surface. So I'm not going to talk about the line, I'm not going to talk about the volume. I only review the part that's the surface part. So for the air. Again, remember that before that we can find the center for the line, and then after that we can find the center of gravity for the volume. But let's just stick to that because this is the part that we need for this section. If I have an object looking like that, it's going to be the x and y axis, and then I have the centroid of that object sitting somewhere here. Usually, the distance for the centroid is referred by prime. So it's going to be the x prime, and this, or bar. What is bar? X bar and y bar. If I have that, I want to find for that shape. I can remember that from the statics. Was the integration of xdA divided by integration or divided by area. Divided by area. If I want to make it a little bit easier to understand, I will go ahead and put the tilde on top of this. X tilde and Y tilde. And X tilde and Y tilde are, so they are coordinates for centroid of element and dA. So if I choose the element dA, the x tilde and y tilde is the coordinate of that element. In other words, if I go ahead and say, if I choose, assume here, this is my dA, if this is the dA, the centroid for that here, it has a coordinate of x. X tilde and y. So for the centroid, especially later on, we use them as a first moment of area when we get to the shear. When we get there, I will tell you how to calculate that. But as long as we know that centroid, we can calculate it. So basically, I'm just writing it here very quickly, but when you get to the shear, I will explain it there. So first moment of area can calculate it as Q about X is XdA the X is YdA. So look at that. What's that integration? The magnitude of that is the x bar times area. Correct? So so it's gonna be y bar area, it's gonna be x bar area. I said you're gonna use that later on in the shear, when we get there. So when we get there, we want to calculate that. What we are gonna do that is that we have to find the centroid and then multiply it by the area. So any question about any of them? So as for regular shapes, so given there's tables in the book that given the centroid for them. But usually when we are dealing with some kind of irregular shapes that we have to deal with. Then it's going to be centroid or so if we have irregular shape, this is how we calculate the centroid. There's no other way but integration. But if we get to the shape like the shape that made of the shape that we already know, so it's made of the rectangle, the square, circle that we already know them, and we can break it down to those shapes. So we are using this method. Instead of doing the integration, we can go ahead and use the, basically convert that integration to sec. So we're gonna change. So if I have a shape that, for example, look like this. So I can break it into the shape that I know. X, Y. I have a shape that. Correct? I can break that into the shapes that I know there's shapes. So for example, I can go ahead and say, hey, I'm gonna, and remember that sometimes there's different way to break them. For example, I can go ahead and say, hey, I'm gonna break that into this and this and this. So break it into 3 areas. One, two, 3. So there are 3 areas that I know their shape. I can recalculate that. Because I can break it into their area that I already know the centroid for them. I know the position of the centroid for rectangle. I know the position of centroid for triangle. So then if I have that, that equation is going to change to, it's going to be sigma x tilde, okay. divided by sigma AI, or basically divided by the total I. And for the y bar, it's the same thing. It's going to be sigma y tilde I AI times the AI, or the entire area. So if I have that, then the same things again. Remember that, again, the x tilde and y tilde are the coordinate of centroid. Coordinate of centroid for the AI. And then the same as there, if I want to calculate the first moment of area. First moment of area is similar to that. Q about the x. It's going to be these two. This time that. There's going to be yi ai, which is going to be y bar sigma ai. And q about the y is going to be sigma AI, the x bar, sigma AI, are the same thing. But right here it's going to be y bar A, it's going to be x bar A. Question up to here. So, for example, I'm going to just write for one of them. You see, it's going to be x tilde, for example, 1 and y tilde 1. So you have one for here, you have one somewhere here, you have one somewhere here. For this part, just remember that for this section, this is going to be the x, correct? for this one, we use one element. To find Centroid, we use only one element to find both X bar and Y bar. Either horizontal or vertical or polar. Horizontal, vertical, or polar. So we can have either horizontal or vertical. I don't write the polar, or you can have the polar elements. For now, I'm not gonna. So I only get, either I get the vertical element and calculate both X bar and Y bar from that, or I get one horizontal and calculate one. So I'm not gonna get one for the X bar and one for the Y bar. You got that? I just use one element. Depend on the shape. Maybe it's easier to get it vertically or horizontally. But whatever you get, assume here I draw it vertically. I get one vertical and use for both of them. Remember this. If we have dx in dA, then we should write all formula as a function of x. If we have dy in dA, then we should write all as a function of So, look at here, if I have the dx in the element, if I have vertical element, so I'm gonna have the dx, correct? Then I'm gonna write the x bar, dA, and a, all of them as function of x. Here and here. X bar, dA, y bar, y tilde d. Everything I will write it as a function of x because I have a dx in the integration. So everything should be as a function of x. If I get the horizontal element, so then they are gonna have the dy in the element, I have to write each of these variable as a function of y. Or basically, we should write all variables, basically. It's better than the formula. All variables. As a function of x and x as function of, or any formula that you have. The point is that we are not going to choose one element for the x bar and another element for the y bar. Whatever element we choose for the x bar, we use the same element for the y bar. Got it? So let's look at the two examples, one for each of them, and then we move up to moment of inertia.
Is that just called E?
So assume I have a shape that looks like this. So I have an area of the cross section that looks like this. It's going to be the X. Going to be the Y. We'll find the centroid for that shape. So the book called it parametrically, it's called it k x to the power of 2. Let's make it, that is, let's call it k x to the power of 2. What number for the k? 5, for example. That's a 5 x to the power of 2. So this is what I have. So the first thing I need to do is that I have to find an element for that shape. Here again, I can get the horizontal or vertical element because one side of that is on the x-axis. It's easier to get the vertical element, so I have the dx there. If it was on the y, I can get also the y element, the horizontal element. It just make it more difficult. So if I get the vertical element, so this is going to be the dx. Now I have to find the centroid of that element. Remember, in the formula is the integration of the centroid of the element dA. Correct? So in the formula, x bar is x tilde dA divided by a, and y bar is y tilde dA divided by a. So I have to find the x tilde, y tilde, d and dA and the a. I have to find those so I can do the calculation. So the first step I want to find this. So this is the coordinate for that. X tilde, so it's gonna be x. So wherever it is, because it's gonna be my x-axis, x tilde. Remember that the coordinate of this point, the coordinate that is on the curve is x and y. The coordinate on the curve is x and y. So the coordinate of x tilde is going to be x because it has the same coordinate as that one. How much the y tilde?
Y divided by 2.
Half of the y. Correct. So now I have the x tilde, I have the y tilde. I need to find the dA also. So look at here. There is dx in. So we have dx in element. So we have to write all variable as a function of x. So x tilde is going to be x. Is already function of x. Correct? I don't need to rewrite. Y tilde is half of y. So I want to write it as a function of x. How do I do that? Y is that equation, so I'm going to replace y with that. Y is 5x squared, so I'm going to say the y tilde is going to be half of 5x squared. Agree? Then what else I need? I need a dA. dA is, how much the dA? Y dx, correct? Because the height of the element is y, the width of it is dx, so it's going to be y dx. Again, I have to rewrite it the same way. So y is 5x squared. So dA is going to be 5x squared dx. And what about the a? A is just the integration of dA, correct? So anywhere I have a, I can replace it with the dA. So agree with them? So now that I have them, I just need to substitute it in that equation. So I need size, so assume this length is, for example, assume it's 10. Okay, assume that's 10. So the x bar is going to be the integration of the x is going from 0 to 10 and the x bar is the x, and the dA is a 5x squared dx, and the area is again 0 to 10 dA, which is 5x squared dx. Same things here. It's gonna, again, I'm just using the same element for both of them, 0 to 10. Y tilde is half of 5x squared, so that's the y tilde, and then the dA, which is gonna be 5x squared dx, and the area is gonna be the same, 0 to 10, 5x squared dx, and then you just need to plug in your calculator, because I randomly choose the numbers, I don't know the answer for them. Seven, 1.5, and
150.
150.
I got like 150.
Oh, 100.
Yep.
Okay. Maybe instead of 5, we should have chosen 1/5. Anyway, so the entire point for it is that you have the dx, write everything as a function of x. If you have a dy, write everything as a function of y. The integration part is the easiest part, you just need to plug in your calculator. So that's the, if you have the shape that does like that. But if you have a shape that made of known shapes, how we can do that? I'm gonna, they have it, I'm gonna make it a little bit simpler. The example they have. So assume I have a shape look like this. X is want to find a centroid for that. So this is 60. This is 80 millimeter. This is 120. Proportional. Let's make it a little bit proportional. So if it's 80, let's say it's 80 and 60. So it's not very well scaled. Well, I assume these are the dimensions. So if I have that, I want to work on that, I can break it into 3 shapes that I know. What are the 3 shapes? I can break it into I can go ahead and say this is equal to the rectangle. Plus minus the circle. So what is going to be this one? So anywhere that I have the area is going to be plus. Anywhere that I don't have the area, or the hollow is going to be minus. My axis, again, going to be x and y, and this is going to be the x, and this is going to be the y, and the same here is going to be the x and the y. So all I need to do, the procedure is a little bit tedious, but all I need to do is that I have to go ahead and find the centroid for each of them. So the centroid for this one is assume this is the one. So centroid for this one, if 120 is going to be 60, and if it is 80, it's going to be 40. Correct? Centroid for this one, remember that the centroid for the triangle, 1/3 from the base. So if this is the 2, still 2. So x tilde is gonna be 1/3 of 120, and y tilde is gonna be 1/3 of 60, negative 1/3 of 60.
40 and negative 20.
40 and negative 20. That's gonna be 40. That's gonna be negative 20. Now minus this one, so the centroid for the circle, if this is a 3, so x tilde 3, y tilde 3. So the x tilde is going to be 60, and the y tilde is going to be 50. So now I need to calculate, remember the equations are x bar is sigma x tilde I AI divided by sigma AI, and y bar is sigma y tilde I AI divided by sigma AI. So I have to find all the AI and all the XIAI and add them together, and the same here, all the AI, all the YIAI, and add them together. So I'm gonna just make a shape here. So I'm gonna say so shape 1, 2, and 3, and then I have the area for them. So for the first one, it's gonna be 120, 80 times 120. For the second one, it's gonna be half of 60 times 120. And for the third one, for the circle, it's gonna be pi, and how much the 20 squared. Agree? So A1. Then I want x tilde. So for the first one, so it's going to be 60, 40, and 60. Y tilde is going to be 40, negative 20, and 50. And then I have x tilde I. And y tilde. So one other thing is that I want to mention, the area that we calculated. So for the rectangle is the real one, for the triangle is the real one, for the circle we don't have it, it's the whole. So it's gonna be negative. And then for the area I'm gonna have, so this is 60 times 80 times 120, and here I have 40 times half of 60 times 120, and then I have 50 times negative pi 20 squared. then when I have them, I have to find sigma A. I have to find sigma x tilde A or A tilde, and I have to find sigma y tilde A. So I can add each of the column, so find these three and then substitute them in those two equations.
Your x of a for shape 3, you wrote times 50 when it's supposed to be times 60. That leading number.
Okay, that's good. Thank you. And then we just substitute it into that equation and it gives us. So 2 points here. Remember that I'm gonna make also that red. If the centroid is in on the negative side of the coordinate axis, so the centroid is gonna be negative. So if it's on the negative part, make sure that's negative. And if it is the whole, make sure it is negative. So, any question about the procedure? We probably don't use that method much, but most of the case we have is gonna be something like that. So, usually with any problem, the very first step is that you go ahead and find the centroid, and the next step is you go ahead and find the moment of inertia. So, any question about this process here? So now let's go and take a look at moment of inertia. Again, similar to the centroid, the moment of inertia, we can use it for the general shape that we have, and then if we can use it for the composite body. is similar like what we had before, so I assume I have again a shape. Cross section looks like this. That's gonna be X and Y. And we'll want to find the moment of inertia about X-axis or Y-axis. First of all, I will write the I about the X. So I about the I about the X-axis is given as with equation y squared dA. If I want to find it about the so if I want to find the Ix, this, remember for the centroid, I can choose either vertical or horizontal element and use it for both of them. For moment of inertia, I cannot do that. For moment of inertia, the element I choose should be parallel to the axis I want to find the moment of inertia about that. So here I want to find the moment of inertia about X, correct? So my element should be parallel to the X. So in this case, I have to choose an element look like this. It's gonna be dy. And that's gonna be the dA. Now if I have the same shape, here, I'll find X, Y, and I want to find the moment of inertia about the Y, so the I about the Y is going to be X squared dA. Now this time I want to find the moment of inertia about Y. So the element I choose should be parallel to the Y. So it's going to be dx, and this is going to be dA. So to find moment of inertia, we have to choose an element parallel to axis we want to find moment of inertia about that. So if we want to find the moment of inertia about the X, we have to choose an element parallel to X. If you want to find it about Y, you have to choose the element about Y. And again, similar to previous one, if you have dx in the element, we have to write all the variables as a function of x. If you have the dy in the element, we have to write all the element about y. So so here we have dy, so we have to write everything as a function of y. Here we have dx, so we have to write everything as a function of x. Okay, so we have dx in element, we need to write all variables as a function of x. And if we have dy in element, we need to write all variables as a function of y. Similar to what we did before. But for the centroid, we just need one of them to calculate both. Here, we have to have two different elements. So the amount of work is basically doubled here. So if you have the moment of inertia, if you want to find the moment of inertia about the general cross section, assuming we have a beam or column or element we are designing that has a cross section look like this. Which usually in probably 90% of the time we are not designing something that have a cross section like that. What we are designing most likely is gonna have a known shape. It may happen, for example, you might need to design the oval shape or something that not regular cross section wise, but usually the one we are designing is kind of known shape. And the polar one we use it in torsion. So if we have the moment of inertia for so again, similar to the previous one, if I had a shape like this, I want to find the moment of inertia for that. I can go ahead again and break it into known shape. So that's just the 1, this is 2, this is 3. So if I want to find it, I know that it's I about x is I of about x for the first one plus I about x for the second one plus I about x for the third one. And the same I about y is I about y for the first one plus I about y for the second one plus I about y for the third. So unlike the Centroid, I just break it, find the I for each of them, and simply add them together. Okay? There is one rule that I want just to mention, that is the parallel axis theorem. It says that I about any axis is equal to I about centroid plus the A d squared. So if I have a shape like this, and there's the x and y, and then I have the x prime and y prime, and then I have this distance is going to be d in the x direction, this is going to be d in the y direction. So if I want to find the I about x, is I about the x prime plus a d sub y squared. And if I want to find the I about y, is I about the y prime axis plus the area times the distance between the two axes, the power of 2. This is a very important rule. We are going to use that over and over again. rectangle. That's gonna be B H. Gonna be X. This is gonna be Y. Y prime. For the rectangle, I about X is 1/3 of BH cube. I about Y is 1/3 of HB cube. I about X prime is 1/12 of BH cube. And I about Y prime is 1/12 of HB cube. Try to, you don't need to memorize it, but because they're gonna use these two so many times, they're gonna just easier to remember. And there, if you remember one after the other one, just replace the B and F. So about the X is 1/3, about the X prime is 1/12. Question? So let's look at one, as I said, you're probably not gonna use this method for the moment of inertia, so I'm gonna just do an example on that, to give you some idea what you're gonna do. Let's make up an example. So, assume I have a shape look like this. x and y axis here. It's going to be x. It's going to be y. And so this is 100 millimeter. So this is, let's say, 40. So I want to find the moment of inertia for that about the x and y. I want to find the I x and I y.
Do we need to know the width of that middle section? Or
Oh,
is that
yes.
something we should be?
Yeah, we need to know that. So I assume that's also 10. Thank you. So if I want to find the moment of inertia for that, I have to find the moment of inertia for each of those sections about the x. So I have to go ahead and start to break it down into the shape I know, find the moment of inertia for each of them. So the easiest way that I can break it down is that I go ahead and break it here and here. Top, middle, bottom. So I can go ahead and say, hey, I can break that into 3 shapes. So I can say it's equal to top part, a bit lower, so I mentioned there. The top part, the middle part, and then the bottom part. This one plus this one. So the x is gonna be, again, assume this is gonna be the x axis, it's gonna be here. The x, y. For this one, the x, y is gonna be here. For this one, the x, y is gonna be correct? So for each of them, I know the moment of inertia about their axis passed through the centroid. But about the x, I don't know how much is that. So I have to find the moment of inertia about their centroid and then use this equation to find it about the x-axis. So for each of them, I have to find their the distance from its centroid to the x and y axis. So if this is the x prime and this is going to be the y prime. So how much is the dx here? So d sub x is 0, correct? Because y prime and y are on top of each other. D sub y, how much is the d sub y?
50.
It's a 4D
Oh, good, yeah.
and 5, yeah. From here to here is 4D, correct?
Yeah.
And from here to the centroid is gonna be 5. So it's gonna be 45. Agree? For the next one, the x prime and y prime is where on top of x and y, correct? So the dx and dy is, both of them is gonna be, so d sub x is 0, d sub y is 0 as well. And remember, these are d sub y, so it's the distance in the x and distance in the y. D sub y is 0. For here, the x prime and y prime, so it's gonna be x prime, that's gonna be y prime. Again, the dx is 0 because y prime and y are on top of each other. D sub y, how much is the d sub y?
Negative 45.
It's a negative 45. Which here, because the distance would be a square,
Oh,
it doesn't matter. So, because most of them would be. So now I want to write it for the first one. So for the first one, I want, so if I say that is 1, that is 2, and that is 3. So for the 1, I about x for the 1. I about x for the 1 is I about x prime versus centroid plus a1, and this is the, which one? D sub y for the 1 square. Correct? So how much is it gonna be? So I about the x1 is gonna be, I about the x prime, how much is the I here? 1/12 of bh cubed. So it's gonna be 1/12 of b what is 100, h is 10 cubed. Agree? Plus the area, which is gonna be, area of 1 is gonna be 100 times 10, and the distance between the axes, which is gonna be 45 squared. I about y for the first one is I about y prime for the 1 plus a1 dx squared. So I about the y1 is gonna be, so about the 1 is gonna be 1/12 of, this time 10 times 100 cubed. And the area, 100 times 10, the distance, 0. So that's the first one. So I have to do that. So for the second one, ix for the second one is the ix prime for the second one plus the a2 dy2 squared. I about the y2 is gonna be y prime 2 plus a2 d x. So ix2 is gonna be, for the second one again, 1/12 of b, which is 10 times 80 cubed plus the area, which is gonna be 10 times 80 times 0 squared. I just write that part so you know that's gonna be 0, but when you get comfortable, you don't need to write it. And for the I about y, it's gonna be 1/12 of 80 times 10 cubed, again plus 10 times 80 times 0 squared. And for the third one, plus a3 dy3 squared. y3 is I, y prime 3 plus a3 x3 squared. So ix about for the third one is 1/12 of the width of that is 40 times 10 cubed plus 40 times 10. This is the area times the dy, which is going to be 45 cubed. And here I about y3 is 1/12 of 10 times 40 cubed plus 40 times 10 times 0 squared. And then when I have them, the ix, I about x is I x1 plus I x2 plus I x3, and I about the y is I y1 plus I y2 plus I y3. This is what we are, this probably we are gonna do for when we get to bending and the shear. Again, this is gonna be the very first step of the entire problem. So you have to go ahead and calculate the moment of inertia for the shape, the cross section you are given before we can calculate the stress. So any question about these processes? Okay then. So next time we will start to look into bending.